In this lecture, we'll use the Born-Haber Cycle and Hess's law to calculate lattice energies. We'll do this by defining the lattice energy, exploring periodic trends for lattice energy, then writing out all of the steps for the Born-Haber Cycle. Let's begin. Consider the formation of solid potassium chloride from its elements in their standard states. We see that the overall process is exothermic at negative 437 kilojoules per mole. We know that potassium has to give up an electron, and chlorine has to accept an electron, but the IE and EA only describe energy changes for particles in the gas phase, where there are few interactions between particles. In the solid phase, there are many interactions between oppositely charged particles as the solid KCl lattice forms. Until we consider those interactions, we won't be able to calculate the enthalpy of formation accurately. We see that the missing quantity that describes the favorable formation of the solid lattice of alternating potassium cations and chloride anions is the lattice energy. Formally defined, the lattice energy is the energy released when gas phase ions coalesce into a solid ionic compound. Note how we describe this in the equation here. Since the energy is released, this will always be an exothermic process as indicated by the negative enthalpy term. What if we considered the formation of a magnesium oxide lattice? Which equation shows the correct way to indicate the lattice formation? The best answer here is C. We're looking for gas phase ions reacting to form a solid ionic compound. The tricky part about lattice energies is that we don't have any way to isolate this specific energy quantity from the overall process of lattice formation. What we can do is take the values we've measured by other means, including the ionization energy, the electron affinity, bond energy, and enthalpy of sublimation, and use these quantities to sketch a cycle where the endothermic processes have to balance out the exothermic ones. The missing quantity will be the lattice energy. Let's take a look at one of these sketches, known as a Born-Haber cycle. We know that the lowest energy state will be the solid KCl lattice that is formed, down here. As we saw in the first slide describing this reaction, we know the enthalpy of formation for KCl, the ionization energy, and the electron affinities. Let's see how those quantities fit into this diagram. The first quantity to add to the diagram is the enthalpy of formation of KCl solid. We know this piece is a part of the energetics of the reaction, but we actually need to use the reverse of the enthalpy of formation to help explain our observations. So step one will always be, take the reverse enthalpy of formation for the substance. Step 2 requires us to sublime solid potassium to the gas phase. Then step 3 will ionize the gas phase potassium atom into a gas phase potassium cation and an electron that can be transferred to the chlorine. Now that we have gas phase K+, it's time to work on our diatomic chlorine to get it in the proper form. In step 4, we break the chlorine-chlorine bond. You'll want to put an asterisk next to this step in particular. Bond energies are often given for 1 mole of the diatomic molecule. If that is the case, then you'll need to take half of the bond energy. Here I've already done this step so that we have half of the bond energy for Cl2. At this point, we've created gas phase K+ and gas phase atomic chlorine by adding energy into the system. The next step, adding the electron from potassium to chlorine, is the first step where we get to release some energy. This is shown in step 5 as the electron affinity for chlorine. The difference between these 5 steps where the energy is known and the actual energy of the ionic lattice formation is the lattice energy. Please review this slide and the ones after it so that you can sketch a rough Born-Haber cycle and know how to adjust the energies to calculate a lattice energy. Recall that the tricky spots occur in step 1, where we have to reverse the enthalpy of formation, and in step 4, where we must take half the bond energy. Make sure you can identify each of these reactions as well. Alright, the final step requires us to add all of these quantities together, then add a negative sign to the result to reflect the fact that this is an exothermic process. For the purposes of the exam, I want you to be able to do this calculation for a +1 metal cation and a halogen, just like we've done here. There are certainly more options, including the formation of magnesium oxide or calcium fluoride, that you may see in practice problems or in the homework, but I'm only asking for mastery on this simplest case. Let's try an example. Can you calculate the lattice energy for a generic MX compound where M is an alkali metal and X is a halogen? Note that half the bond energy and the reverse of the enthalpy of formation are given. The Born-Haber cycle for this generic process is given to assist in your calculations. It's a good idea to memorize this generic cycle for the exam. Alright, the answer to the last question is negative 788 kilojoules per mole of MX formed. Taking a step back from the Born-Haber cycle, we can compare a series of alkali metal and alkaline earth metal compounds to look for periodic trends. For example, lithium compound's lattice energy decreases as you move to larger anions from fluorine to bromine. This trend is repeated for the sodium and potassium compounds too, so anion size has something to do with lattice energy. If we look at the chloride compounds of magnesium, calcium, and strontium, we see that increasing cation size has the same effect. Larger cations result in lower lattice energies. Or if we compare the lattice energy of sodium chloride and calcium chloride, it would seem that calcium with its +2 charge has a much larger lattice energy than sodium with its +1 charge. So what explains these observations? You won't be expected to calculate this, but the equation relating the charges of the ions Q1 and Q2 divided by the distance between the two charges is helpful in rationalizing the observed periodic trends. Using the Q1, Q2, and D relationship, we can explain how lattice energy decreases going down a group since the radii of the cations and anions will increase. For example, using the chloride ion as our constant, we can see that the ionic radius increases down a group as we track from lithium to sodium to potassium and to rubidium. Since the distance between ions is the denominator of the charge-distance relationship, lattice energy will decrease as the distance increases. We can also examine the effect of changing the charge while holding the distance fairly constant. Lithium fluoride has a lattice energy of negative 1030 kilojoules per mole, while magnesium oxide with its +2 cation and -2 anion has a lattice energy almost 4 times that of lithium fluoride. Therefore, increasing charge will increase the lattice energy. Use ionic charge to order the compounds in terms of increasingly negative lattice energy. Both sodium fluoride and cesium fluoride are composed of +1 cations and -1 anions. These will have lower lattice energies. Magnesium chloride contains a +2 cation and a -1 anion, so its lattice energy is higher than sodium fluoride and cesium fluoride. Scandium nitride, SCN, contains a -3 anion, so it must also contain a +3 cation, giving it the highest lattice energy. Now, use ionic size to determine whether sodium fluoride or cesium fluoride has a smaller, less negative lattice energy. Cesium plus is larger than sodium plus, so sodium fluoride has a larger negative lattice energy than cesium fluoride. Finally, place all 4 compounds in the correct order of increasingly negative lattice energy. Cesium fluoride is less than sodium fluoride, is less than magnesium chloride, is less than scandium nitride. Here's one for you to try without my help. Which compound is likely to have the most negative lattice energy? The best answer here is B. If we split these compounds into groups by anion, we see that fluoride is smaller than chloride, so we'll expect the fluorides to have larger lattice energies. Between sodium and magnesium, magnesium has the larger charge and will have the larger lattice energy. Finally, I'll leave you with the parting thoughts of the authors.